Welcome to the first of four videos to help you walk through some of these practice problems. Rather than just giving you the solutions, I figured it might be nice for you to see, and as I'll talk through the process of trying to solve these problems, what I'm thinking and what you guys should be emphasizing and looking for in a problem. So you can get a link. If you look at the description of this video, there's a link to a PDF file where you can print out these practice problems, or this one practice problem, and we'll have a PDF for each one. So let's take a look at this first one. We've got a seesaw or teeter-totter problem. You've got the mother on one side, Sharon, 240 kilograms, and then you have her three sons over on the other side, 30, 44, and 28 kilograms. As you read through the paragraph, you see that the other given information, you've got a 4-meter long teeter-totter, and you've got a 0.5 meter increment from the opposite end there. So you would have the 30 kilogram child at the very end, and then 0.5 between that child and the 44 kilogram, and then another 0.5 meters between the 44 kilogram and the 28 kilogram. And what Sharon did, if you read through the problem, it says she does a few quick calculations, a few measurements, and she figured out where she should place that fulcrum. So she slid the seesaw back and forth so that when she sat on one end, the three students or three children on the other end were balanced out perfectly to make it the best experience possible. So I'm going to switch over here so I have enough room to solve the problem and start sort of diagramming out what kinds of stuff we know. So let me get my pen going here. Alright, so we know, first thing is that from end to end, we know that the total distance is 4 meters. Right? And we know between each one, and I'm going to go from the center of each, we've got 0.5 meters. Alright, and all this information is in the paragraph part of our problem. And then we have a distance that we're looking for, x, for where Sharon is actually going to sit. Right, and then we that's pretty much it. That's the information that we have. So we see obviously that it is a teeter-totter problem, so that should hopefully direct you towards a equation using the sum of the torques that are acting in the problem. And since we are looking for her being balanced, we see that that those net torques should equal 0. So if we kind of get our feet in here and start working with the problem, we can see, okay, if she's going to be x distance away, then that means, again, if I don't know, this looks like it's in the middle, but it may not be. In fact, it won't be. We're looking for where it should be. So we need to know, if we're going to do this net torque equation, we know the torque equation is force times distance, or force times radius, times the sine of the angle. Now, all of these angles are 90 degrees, so we're not going to worry about that since the sine of 90 degrees is 1. And we're going to go through and we're going to then need to figure out what these radii are going to be. So for this first one here, this 30 kilogram son, we have that is going to be 4 minus x for the distance, right, to that son. Then since this son is 0.5 meters closer to the fulcrum, we would have a radius for this son to be 3.5 minus x to get to the fulcrum. And then for this last son, again, another 0.5 meters closer to the fulcrum, that's going to be 3 minus x to get there. Okay, so those are going to be our radii for all the students, or sorry, all the sons, and then you have x being the radius for Sharon, the mother. Alright, so that's all the information really that we need. Now it's just a matter of setting up our torque equation, our net torque equation. So I'm going to work my way from the left side to the right side, placing my pivot point there. Right, that's the pivot point that I chose for this problem. And what we're going to do is I'm going to set it up as a net torque. We can set it up with the equal sign in the middle. Some of you might be familiar with that, but I wanted to show you it doesn't matter how to set it up. We'll set it up as we do on all of our other problems as a net torque problem. So I'm going to have, first I need the force of the 30 kilogram sun. So I do 30 times 9.8, and that'll give us the force for that sun. And then the radius for that sun is 4 minus x, right? And that is going to be a counterclockwise torque, right? That's going to cause a motion in the counterclockwise direction, since my pivot point is on the fulcrum there. So that's going to be a positive. So really all of these are going to cause a counterclockwise motion, since all of them are gravitational forces. They're all pulling in the downward direction. So I'm going to have plus 44 kilograms. Oops. 44 kilograms times 9.8 times 3.5 minus x. And then for the last sun, 28 kilograms times 9.8 times 3 minus x. Alright, and then for Sharon, her gravitational force is going to go down this direction, so that's going to be a clockwise rotation. And the clockwise rotation is going to be a negative torque, so it'll be negative 240 times 9.8 times x. Okay, so that's the setup. That's really all the physics there is. From here on out, it's just going to be algebra. So let me go ahead and do that. Alright, so that means that the distance between the pivot point and Sharon from here to here should be 1.05 meters, and that's the answer. Hope that helped.